Rajiv Asthana sir, who is back with us for today's next technical session. In this segment, sir will be covering two highly relevant, intellectually rich topics. First of all, he'll take us through metal, ceramic, and polymer composites, followed by a session on joining and integrating of dissimilar materials, both of which are essential to understanding the real-world complexities of advanced manufacturing. Sir's ability to bring clarity to complex material science topics, coupled with his global experience in teaching and research, is something we greatly for. So it's a privilege to have you with us here again. We warmly invite you to begin the session.
Hey, good afternoon, everyone. I'm going to talk about composite materials today in this session. So I'm going to look at metallic composites, ceramic composites, and polymer composites. And pretty much all of us have been using composites somewhere or another. So just to get started, let's consider wood. Ordinary wood is a composite, a natural composite, not a man-made composite, obviously, but a naturally occurring composite. So in a composite, you have at least two different phases, chemical phases. It could be one could be fiber or particles, and the other phase could be a continuous phase of the matrix phase. So in the case of wood, the fiber is actually the cellulose, chemical cellulose. So that's the fiber, and then lignin is called the matrix material. The slides are not changing in the online session. But they're not changing then. Okay. बट वॉइस तो आ रही है वो सारी बट इंटरनेट थोड़ा सा solution in internet. Okay. Yes, that's okay. Instagram slide. And then arrow से change करो नहीं हो रहा उससे मैंने क्या स्क्रीन से ही आ रही है बट चेंज करो स्लाइड हाँ हो रही है प्रेजेंटेशन व्यू में जाओ अब चेंज करें स्लाइड बट ये डबल स्क्रीन है अभी चेंज करें Okay, so I'll use the page down and up for changing size.
Yes, sir. You can also use
I'm used to mostly this,
Yes, sir. Yes, sir.
we can use with this.
Yes, sir. We can.
Oh, so manually I have to do that. Okay.
And
Okay. This we have. Okay. All right. Thank you.
thank you.
Thank you.
Afterwards.
Hi. So let us go back and look at the natural composite that is the wood. And in wood, cellulose is the fiber, and that is what provides the strength and rigidity to the to wood. And lignin is a polymer matrix. So wood is a composite, and you can see at different length scales, millimeter scale, this is what wood looks like. We know that at the micrometer scale, it is a highly porous structure. So this is an SEM image of a piece of wood. You can see a lot of pores in here. And when you go down to the nanometer scale, you actually see the molecular chains of cellulose, which is the fiber, and then lignin and hemicellulose. Those are the matrix materials. So by the way, wood is also used to make ceramic materials. That is something we'll come to later on when we look at ceramic composites. But what people now do is that they take wood and partially burn it, pyrolyze it, to make a highly porous carbon structure. And then they infiltrate porous carbon structure with molten silicon. So silicon reacts with carbon and forms silicon carbide. So that's a very eco-friendly process to make a ceramic from a natural resource like wood. But wood is a natural composite. We are mainly concerned here with synthetic composites or man-made composites. So what are the important factors when you make or design a composite, polymer composites? So these are the key parameters: the concentration or volume fraction of the fibers. So that's one factor here. Size. What is the diameter or size of the particles or fibers? Shape. Are you going to have regular shape or random shapes? How are the fibers distributed in the system? And finally, the orientation of the fibers. If you're using fibers, of course, if you're using particles, then it will be more isotropic. But if you have fibers, then orientation could matter. Are the fibers going to be in this direction or in other direction? So all those parameters have to be controlled in the manufacturing process when you make a polymer composites. And again, just going back to this sketch, which I had shown earlier last time, the main mechanism for strengthening in a polymer composite is transfer of load from the matrix to the stronger fiber. So fiber is stronger than the polymer around it. So under an external stress, the polymer might begin to crack, as we see in this sketch here. But the crack will not cause the failure of the whole component because fiber is well bonded to the polymer and the applied load will be taken over by the fiber. So the part can continue to survive. Here are some actual data on mechanical properties and thermal properties of common polymeric materials. We are looking at the modulus, tensile strength, yield strength, elongation, specific gravity, and other properties here. The main takeaway here is that most polymers are not stiff. Their modulus, elastic modulus, is pretty low, 1/10 to about 2 or 3 gigapascals only. Their tensile strength is also very low. In megapascals, it is a few megapascals. And because of those two limitations, we want to strengthen polymers by fibers. The one interesting thing about polymers is the elongation. Most polymers have very, very high elongation. Percent elongation could be a few hundred or few thousand%. And another advantage of polymers is their low specific gravity. They're very lightweight materials. So for low temperature applications, lightweight applications, one might want to use polymer matrix. These are some data on fibers that are used in polymer composites. different types of commercial fibers, silicon carbide, aluminum oxide, carbon fibers, high modulus fiber, high strength fiber, and then Kevlar fiber. If you look at the properties of these materials, they have very high tensile strength. In megapascal, their strength runs into several thousand MPa or even gigapascal range, which means if you combine these fibers with polymers, you can make a very strong material. Also, the density is not very high. Well, here the units are in kilograms over cubic meter. The previous table had in grams over cubic centimeters. Essentially, you're looking at 3.2 or 3.1 grams over cubic centimeters. So fibers are a little bit heavier than polymers, but there is not a whole lot of penalty on the weight of the composite when you put fibers in the polymers. So that is the main reason why we want to combine these two kind of materials. Some actual commercial fibers and fabrics that are used in composites, polymer composites. Kevlar is a polymer fiber, aramid fiber. So most often we don't use single fibers. We create a cloth or sheet or a mat out of fibers. And this is where textile engineering expertise comes into play. How are you going to weave the cloth to create certain patterns for properties? So we have Kevlar fibers, carbon fiber sheets, silicon carbide, or commercially called nickel-on fiber, fiberglass. Some commercial fibers are not single phase. For example, a commercial fiber called Borsic is a boron silicon carbide fiber. So the core is boron, it's a boron filament, and on top of it, we have CBD coating of silicon carbide. So there are some commercial fibers that they are themselves composite materials. And when you put these composite fibers in a matrix, you make very strong. Aluminum oxide. So all of these and many others are commonly used. And as I just mentioned, the fiber cloth could be very complex. And there are ways to design fiber cloth to get certain properties. The fibers could be mostly ceramic materials, but sometimes metal and polymers are also used in fiber form. Some commercial fibers are used there. But if you look at the stress strain behavior, obviously ceramics are very strong. They don't have any plasticity. Plastics and other things. So fibers that are available in the market are made out of ceramics. And if you look at the tensile strength versus elongation data, this is a graph I showed last time also. But if you look at these data, you can see that the tensile strength can approach 20,000 megapascals or about 20 or 21 gigapascals, especially if you put whiskers in a polymer matrix. Again, whiskers are single crystal short fibers of ceramic materials. So there is a very high strength. But even if you're not using whiskers, common fibers like boron fibers or HMG, which is high modular graphite fiber, aramid fiber, glass, all of these have very high tensile strengths on the order of a few thousand megapascals or gigapascals. So when you put these fibers in a polymer, you can make the polymer extremely strong. What are some common methods to make polymer composites? There are a whole bunch of those. Injection molding is very commonly used. Basically, you inject a molten polymer in a die in which you already have a prefabricated fiber preform. So under pressure, the liquid polymer will combine with the preform, and after cooling, you will get a composite material. Another method is pultrusion, which is basically a combination of pulling and extrusion process. So in this process, fibers are pulled through a resin and then a die, and then they're cured. This is a fiber bundle, carbon fiber bundle, for example. It goes through a tank in which you have resin. So you get a coating of resin on the fibers, and that coated fiber goes through a die where it is actually shaped in a part. And then the shaped part goes through a curing die where the polymer is cured to make the final composite material. Compression molding uses curing of the polymer matrix under high pressure. So the pre-preg, which is basically the laminate or pre-form of the fibers, that is placed in a die, and a resin is introduced in the die, and then under high pressure, the resin is cured until it hardens. And one can also use hand layer procedures to make polymer composites, which means you lay the fibers and manually apply resin, either by spraying or with a brush or other methods. And then filament winding is used mostly to make cylindrical structure of composites, pipes and pressure vessels and tubes. So in this case, fibers are wound on a rotating mandrel, and those fibers are coated with a resin to make the final part after curing. The interesting thing about polymer composites is that you can actually lay the fiber or pre-pregs at different angles to get different properties. So the top here, for example, has 0-degree angle. 0-degree means that this lamina or this pre-preg is in the direction of the fiber. Now the next sheet would have 90 degrees, which means fibers are perpendicular to the previous orientation. Okay, 0, 90, 0, 90, this kind of an orientation, or many other kinds are possible. You can also create sandwich panels, means you can have honeycombs or hollow sections in between. If you're making this kind of a part, and this is corrugated part, these kind of things are very commonly used in packaging applications also. But all that you need is a honeycomb structure and face sheets of polymer and an adhesive sheet in between. So many of these processes can give you composite design properties. Here is an example of how you can design the thermal expansion coefficient of a polymer composite just by changing the orientation of the or pre-preg. Can even give you a negative expansion coefficient. So this is 0 expansion coefficient, here -5. So you can see that you're coming down to negative expansion coefficient when you have certain orientation of the fibers. So the main message here, you can actually do polymer composites for specific properties, thermal mechanical strength, stiffness, and other things. Here are some math on mechanical properties. First graph, the tensile for glass fiber reinforced epoxy. So you're looking at the effect of % glass, 0%, 20%, 30%, 40%. So as you can see that as you increase the percentage of glass fiber in epoxy, the tensile strength increases, but percentage elongation decreases. So there is a trade-off between strength and ductility for composites. The second graph shows some other properties of composite. Here you look at fiber oriented glass. Looking at the 20% of the property. Looking at specific gravity, elastic modulus, and isotope or impact energy to bring. And again, we see here that the modulus increases the glass. And epoxy have very similar density values. So by changing the amount of glass fiber, you don't the density. There is the weight of the energy or toughness drops as you add more fiber because glass is more it is more brittle. Let's put it that way. So, and we all know the difference between strength and toughness. If you take if you take a piece of aluminum, you try to scratch aluminum and glass with a knife. You'll be able to scratch aluminum, but you won't be able to scratch glass. But do another experiment, drop glass from the glass matter, experiments, what are really characterizing. In one case, I'm able to scratch aluminum, but when I drop aluminum in glass, aluminum doesn't, glass breaks. Right? So when you're trying to scratch aluminum in glass, we looking at properties. And does not be measured how much energy was used up in breaking. And we know that energy in force and just mention something under force to this point, or either energy is more glass fiber in it. In the we are looking at this modulus fiber to reinforce glass, not short fiber, but continuous fiber. And you can see that the modulus and strength they depend on the orientation of the fiber. So if you look at the number in the first row, second row up here, 45 with the parallel means this is the value of the modulus in the direction of the fiber. 12 is the mechanical property. It allows you to predict mechanical properties, especially of composite, just by knowing modulus of the between polymer property could be of the individual constant. So the direction you're measuring fraction behind the modulus matrix. As the direction, we should assume different formula. If you look at the experiment, come accurately with the formula. So the mechanical predicted the modulus. Used in all applications. I would make package automobiles, example as shown items to the picture of with carbon particles added to rubber, and this is size. These make rubber and the resist rubber under. Second example of it is a double. We have pressurized layer at the polymer light inside the rubber. So that composite layers outside. So polymer kinds of application fields are made in carbonate or nine. Some of these fibers. Similarly, picture of have parts made graphite fiber. So even though the is part so I think start review some Test. See, so this to them. So it's okay. अभी just next to use this. Please go for you. Okay. Hit and the zoom in. Okay. All right. Look at composite material, metal. As the name tells, composite kind of materials, and they have been used in many things. Looking at left and the content made in the second column. So, there's aluminum factors because the copper is electricity is graphite. It pro benefit. It is a solid. So when you hit powder to so plotting specific stiffness or modulus over the density on the y-axis and specific strength or tensile strength divided by the density of the material on the x-axis. And steel, aluminum, titanium, they fall over here, but composites of aluminum, here are the manufacturers, different countries. But if you look at reinforcement, they are mostly ceramic materials. Oxides, carbides, chloride compounds. Those are the most common types of materials. And again, these are the properties of some fibers and matrix materials. We don't have to look at all the details, but just let's see some general things here. Density. Fibers are pretty light compared to metals. So there is no disadvantage in terms of weight. For example, you have nickel, steel, and superalloys. These things are pretty high density. Even copper, 7 or 8 grams per cubic centimeters. But when you add fibers, fibers are much lighter. So when you add fibers or even particulates, you actually have benefit of lightweight and other benefits like high strength. So that is why we make what are some common methods available to manufacture metal composites? There are too many, and I didn't want to put the sketches or pictures, so I'll just talk maybe 1 or 2 sentences about each. And then later, if anyone has questions, we can discuss more about them. So one simple method is carrier gas injection. If you want to add graphite powders to molten aluminum, you will have to first apply some coating, nickel coating to graphite powder, and then use pressurized air to inject graphite powder in molten metal. That injection process will create slurry that can be solidified. Another method is mechanical mixing. By the way, this carrier gas injection method was the first one used to make composites before stir casting. Sometimes in the 1960s, this process was used. Mechanical mixing, which is stir casting, uses a mechanical impeller in a molten metal. The thing is that most ceramic powders, they behave like plastic beads in water. If you add plastic beads in water, they're all trying to cluster together. So same thing happens with graphite powder or other ceramics in metal. So you have to stir, but stirring is not alone. You have to have either coating supplied to powders, or you may have to add magnesium or other reactive elements to uniformly disperse the ceramic powders in the metal. But mechanical mixing can be done. The problem with mechanical mixing is that even with a ceramic coating on the stirrer, slowly the stirrer will dissolve and contaminate the molten metal. So quite often people use MHD, magnetohydrodynamic stirring, something like simple induction furnace, where you have magnetic field creating eddy currents in the metal, and that creates circular motion. So that kind of an agitation helps in stirring the powders in the metal without any worry about stirrer dissolving or contaminating in the metal. Ultrasound is commonly used, not commonly, but yet it has been used to make composites. So you basically melt the metal or alloy and then add powder to the surface of the molten metal and touch the surface of the molten metal with a titanium horn through which you pass ultrasonic vibrations. So the cavitation process will generate very high accelerations, and they will force the powders into the molten metal. So high frequency vibrations are used. The challenge with ultrasound is that it's not very practical method for large castings. And if you are making a 100 or 500 pound casting, then it is okay. But in industry, you pour castings that are 5,000 pounds or 7,000 pounds. So just using one transducer or one probe will not give you uniform distribution, because vibrations will dampen out as sound waves propagate in the liquid. So you will have to have many probes around, and that will add to the cost of the process. So ultrasound is used for small scale, not for large industrial castings. So these top 4 methods are just methods to introduce reinforcement in the metal. The remaining methods down below are solidification processes to make the actual composite. So sand and permanent mold casting is used. Centrifugal casting is used, in which you pour a mixture or a slurry, and then the density differences will cause the reinforcement to segregate in some areas. Semi-solid casting and thixoforming. You add powders of ceramics to a molten alloy and then control the temperature of the alloy so that it's partially solid. And then you die cast it to make a composite. When you have an alloy in a semi-solid state, temperatures are lower as compared to a fully liquid alloy, which means there is less hot corrosion of the die, less thermal fatigue, and other benefits also. Pressure die casting is used to make composite. Also, pressureless spontaneous infiltration. There have been many attempts and many patents were awarded to different companies to make composite by self-infiltration. Especially, I remember in the United States, there were companies that manufactured composites using self-infiltration in a controlled atmosphere. The whole trick there was to promote wetting so that the liquid will wick automatically in a bed of powders or fibers. Gas pressure infiltration uses high pressure of an inert gas or even nitrogen sometimes to pressurize molten alloys through a bed of powders or a bundle of fiber reinforcements. Squeeze casting uses an actual piston or a plunger, squeeze molten metal inside the fiber bundle or powder bed. So in squeeze casting, you are able to get to higher pressures as compared to gas pressure infiltration. In situ fabrication processes create the reinforcement inside the metal itself. In other words, you don't add any reinforcement externally. You choose your alloy in such a way that chemical reactions of the constituents will form the reinforcement. So some directional certification processes utilize in situ fabrication of reinforcement. And then you have spray forming. That means you spray molten alloys over fiber bundles, or you spray molten alloys over a bed of powders and then hot press everything to create a composite. So again, this is not just a complete exhaustive list. People have come up with many innovative approaches. There are combination approaches also. Just skip. These are just the type of composites people have made using different fibers and metals. These are examples of composites made using ultrasound. All different kinds of materials were made. These are examples of infiltration. I'm sorry, in situ composites for different industries. One thing with fibers is that when you add fibers or even particles of a ceramic to a metal or alloy, you sacrifice the fracture toughness to an extent. Because metals have higher fracture toughness, but ceramics have very poor toughness. So when you combine the two, you lose some toughness, but you gain strength and other properties. So the trade-off between strength and toughness has to be kept in mind when you select composites for specific applications. People have also made hybrid metal matrix composites. Currently, there is a lot of push to make composites by using different types of fibers or particles. But earlier, people were also making fibers, mixing fibers with particles or viscose. So the same raw material, but different shapes and different sizes mixed together to make composite. And very, very high strength could be obtained for some of those. Again, thermal expansion data, thermal expansion properties depend on the amount of reinforcement. We know that ceramics have lower thermal expansion properties as compared to metals and alloys. So when you combine the two, you get less or lower thermal expansion, which may be good or bad depending upon your need. If you want less dimensional changes during temperature change, then you have, a composite will be a benefit. Coatings are used on reinforcement to help transfer them into the molten alloy. And you're looking at some images here of nickel-coated silicon carbide. So these dark particles are silicon carbide particles. They have a nickel coating on them. And in between, you have the nickel, have aluminum alloy. So this is a pressure cast aluminum composite in which you have nickel coated silicon carbide. Because of the nickel coating, the bonding is very good between the two. If you did not have this coating, then bonding is not very good. Same thing you are seeing with fibers, silicon carbide fibers with nickel coatings. So quite often you apply coatings to improve uh, dispersion of fibers in metallic matrices. Here are some microstructures of metal matrix composites. You can get silicon carbide aluminum composites. In most cases, especially when you're dealing with particles or short fibers, in most cases, particles and fibers are pushed in the last solidifying area of the composite. So if you're using a casting process to make a composite, as aluminum dendrites or cells form, they begin to push the particles in the last solidifying eutectic areas. And that makes it a little challenging because the uniform distribution of particles becomes difficult. One way to handle that is to rapidly quench your slurry so that the grain structure is extremely fine, which means the particles will be relatively more uniformly distributed. Ideally, what you want to do is what is shown in this sketch over here. These are the particles suspended in the liquid here, and this is the growing cell or dendrite. So as the cell grows in the liquid, the particles may be entrapped between these neighboring dendrites, or they can be pushed ahead of this dendrite, which means the particles will end up in these kind of eutectic areas. Ideally, you want particles to be engulfed inside the dendrite. And that can happen, but you need very, very high velocities for engulfment of particles by metal dendrites. So very often we cannot engulf the particles, but we can at least get this kind of a distribution of particles or fibers. And here we are looking at some metallurgical structure of composites. These colors, you can use special methods to color etch your samples. Each of these colors is a different chemical element. So copper, nickel, aluminum, all those will show bands of different colors. And this could give you a very clear visual picture of how microsegregation takes place between particles or fibers. Sometimes you also see some phases, new. In this case, this is a hyper-eutectic aluminum silicon alloy, which means more than 13% silicon, and primary silicon actually nucleates or precipitates of silicon carbide particles. So a lot of things are happening on a microscopic scale in a metal matrix composite, both in a particle system or a fiber system. People have made all kinds of composites. Glass particles, glass fibers have been also put in metals like aluminum. Glass actually gives you good lubrication properties. When you put glass fibers or particles in aluminum, you can use that composite in a friction application. What people observe is this, that because of frictional heat, glass partially surfaces. So particles and fibers in composites. There could be defect forming because if you're pressurizing like this casting, if you're making fibers, the pressure application might kind of bunch up the fiber in certain areas instead of uniformly distributing them. So you can have these kind of channeling effects. So you have to have some special methods, things like fugitive binders that can hold fibers in place. These are some pictures of composites made using powder metallurgy on the top, and the same composite made using metal casting process. In metal casting, temperatures are much higher, so there is a lot of reaction. The fiber matrix is less in powder metallurgy composite. This is again the same thing shown here. In powder metallurgy composite, the reaction layer is thinner, and in certified composite, the reaction layer is thicker. You may also have some shrinkage cracks also in the composite. At very high magnification, you can actually see what is happening at the interface. We will not get into the chemistry details here, but one main point here is the surface of the fiber. What happens to the fiber surface in this kind of a reaction? This is the fiber extracted by dissolving the metal around it. And you can see that fiber is very heavily notched. Is it good or bad? Well, this is what is happening. A certain amount of chemical reaction is important because bonding becomes strong. But if you have too much of reaction, then the fiber surface is degraded. And because fibers are brittle materials, any kind of notch or defect will weaken it. We know the Griffith theory of brittle fracture. We have thin notch and that can weaken the material. So ideally, you don't want to have very severe reaction. You want to have mild reaction, just enough for bonding to take place. I think I might be finishing in a few minutes, maybe 10 minutes or 5 minutes or so.
Yes.
10 minutes or so. Okay, I think so. Yeah, so one can modify the structure of composites, metal composites, using different methods. And by modifying the structure, you can actually make very interesting materials. One of the works I was doing way back 30, 40 years ago was to try to create single crystal nickel superalloys in which I could put single crystal sapphire fibers. So try to get rid of all the grain boundaries and put sapphire fibers in a single crystal nickel superalloy. That would give very, very high strength and creep resistance. This is again just the bond strength situation. You can actually measure the bond strength between the fibers and the matrix using what is called a fiber push-out test. You cut out a very thin wafer from the composite, like a slice like this, maybe 100 or 200 micrometer thick, and then use a micro indenter and push it through the disc here, and record the stress versus strain diagram as the fiber slides out of the matrix. So depending on how the reaction has occurred at the interface, you will get different bond strength properties. So that was one way to actually measure the effect of reaction, effect of processing method on bond strength. And then, of course, you would do the actual mechanical test to check the properties. Oh, this is just my advertisement. These are the books that I wrote or edited, but this is the book I wrote on composites in 1998. After 15 years of work on metal matrix composites, I decided to write a book, about 400-page book. So that is one of my first books here. Anyway, coming to the last topic here, very briefly, I will look at ceramic matrix composites. Ceramic matrix composites are not as widely used as metal and polymer composites. They're mostly used in high technology applications, aerospace and defense and everything. So what is a ceramic matrix composite? A ceramic matrix composite is a ceramic matrix in which you have put ceramic fibers. This makes parts more resistant to extreme conditions and lighter. And ceramic composites overcome some deficiencies of conventional ceramics, that is the low fracture toughness and also the low thermal shock resistance and brittle failure. So those problems of monolithic ceramics can be overcome by putting ceramic fibers in another ceramic. And I had mentioned about the basic idea last time that you want to create a weak bond, not a very strong bond, so that any crack can be deflected around the fibers. What kind of applications are there of CMCs? Mostly high temperature applications, components for gas turbines, turbine blades, combustion chambers, exhaust nozzles, all of those things are now being made. They have just begun to be made out of CMCs, or heat shield systems for aerospace, burners, and also this kind of a braking system is made out of CMCs. And the whole idea for getting high toughness is to be able to deflect any crack around the fiber and delay the fracture of the component. So if there is a crack in the ceramic matrix, and if the bonding between the fiber and the matrix is weak, then the crack will actually meander around the fiber. And then it will meet another fiber, another fiber, another fiber. So the crack will be deflected and the component will not fail for a long time. So this actual microstructure shows how a crack was getting deflected around a second phase of a ceramic material. So that is the basic idea in a CMC. So I think that's pretty much all I have for this topic. And if you have any questions, comments, feel free to ask. Thank you. Thank you.